Hello guys, welcome yet to another video. Today we'll continue with our circle geometry series, and this will be for the grade 12 November 2020 question paper 2 for mathematics. Before we can continue with everything, I just wanted to remind you, please like the video if you find it useful, comment if you have any questions based on what we have explained on the video, on the previous videos, and just share the subscription so that this video may be suggested to many other people in need. Alright, so we are looking at question 10 today. There is a statement, and most importantly there is a diagram. So the statement reads as follows. In the diagram, a circle passes through D, B and E. Okay, they have told us there is a circle and then there are points D, B, E. So the way they've worded the question here, or the statement, is that the circle passes through certain points, and normally we say there's a circle and then there's points D, B and E which are located on the circumference of the circle. Okay, so that was a little bit of a mind twist there. And then there is a diameter ED. Let's look at ED. There is ED. They are saying that is a diameter. So we know that this circle is divided into half. This side and this side. So this is a semicircle. This is the semicircle. When combined, they will make the circle. Alright. They are also mentioning that this diameter is produced to end at point C. So if we look at this diameter ED, it is produced up until the point C. So we're seeing that nice straight line in there. And then they are mentioning that AC is a tangent to the circle at B. There is a tangent, and they are telling us which point in or on the circle does it touch. Remember, a tangent can only be a tangent if it is a line that touches the circle only at one point. If it touches it more than once, then it is no longer a tangent. So which point is this specific tangent AC touching? It's touching B. And they are mentioning that M is a point on DE. There is M, which is a point on that diameter of ours, and DE. Okay, and then they're mentioning that AM is perpendicular to DE. So where we see AM, we are seeing a perpendicular intersection with ED. Alright. Then they are also mentioning that AM and chord BE intersect at F. So we have AM and BE. So these two lines are intersecting at this point F. Alright. Now let's continue to the questions. Alright, the first question, before I put this down, is asking us to prove that FBDM is a cyclic quad. So I'm just going to jot down the question. 10.1.1 FBDM, cyclic quad. That is the question. Alright. As I keep on mentioning on the previous videos, specifically for circle geometry, I'm going to attach more links with this video. Please have a look at those videos because they build up to what we are solving today. So each and every video of circle geometry is a mere build up to the to any other questions that might involve circle geometry. So in this one, we are being asked about a cyclic quad, and you ask yourself, what is a cyclic quad? We have covered that on one of the videos. So the most important thing I want you to take from this one is, now that we know what is a cyclic quad, we must also know how to prove that it is a cyclic quad. Let me repeat that. We know that something is a cyclic quad, but how do we know that? And that is the proof part. So I mentioned that in proving a cyclic quad, we can use different approaches. We can either go with opposite angles of a cyclic quad, those angles should be supplementary. And then we can further look into exterior angles, and the exterior angle needs to be equal to the opposite interior angle. But all of that will need you to look at your diagram and just look or observe what is the best approach. Okay, so to get deep into the cyclic quad, please have a look at the previous videos. In this specific diagram, we are asked to prove that FBDM is a cyclic quad. The first thing is, if it is a cyclic quad, then I might as well try to draw it. I must try to imagine it. Let me make sure that I get rid of ambiguities. I can see that shape of a circle going through those points. And then from there, I can start being creative as in how can I go around proving this. So the first thing is, let's try to draw the cyclic quad on the diagram. They are saying FBDM. So these are the points FBDM. So what's special about those points is, when they say prove that it is a cyclic quad, it means those points must touch the circumference of that specific circle we are trying to prove that this lies on. So when we're drawing the circle, we must make sure that it touches those points. All right, so let's try that. I'm going to draw the circle. There it is. It comes here. There is our circle. The circle starts from F, B, D, and M, and then comes back to F. So FBDM must lie on the circumference of the circle. All right. Now, how do we go about proving that this indeed is a cyclic quad? I said we can look at the opposite interior angles. So these opposite angles should be supplementary. So first approach, opposite angles are supplementary. Second approach is the opposite, the exterior angle of a cyclic quad should be equal to the opposite interior angle. So exterior angle is equal to opposite interior angle. Why do we write these things? It's so that you first determine what makes something a cyclic quad, or what makes that specific shape to be a cyclic quad. And from those two, you can sort of select based on a diagram which is the easiest approach. Like I mentioned, always we want to use the easiest approach, but easy is not the solution. That's not what we always envision our questions to always be, but easy simply means that we have analyzed the diagram at hand. We have looked at various solutions, but what can we take from these and minimize the number of steps and finish and go on to the next questions. So easy in this sense just means that we'll use lesser steps, but the thinking behind all of this is not easy. It requires practice. So let's start with that one. Opposite angles of a cyclic quad are supplementary. So FBDM. We may maybe look at D2 and F4. We must prove that if you are to add these two, they are equal to 180 degrees. But that is tough because we need to find F4. We don't have F4. We don't have F4. We don't have D2. All right. Maybe we can go with the other side. What about adding B2 to M1? Can those add up to 180 degrees? So we see that there is B2 and then there is M1. Okay, do we have B2? No, we don't. How can we go about finding B2? So you ask yourself, what is special about B2? B2 is, so every time we're about to solve for an angle, I always mention on the previous videos that ask yourself, where is that angle located? So find the angle, look at the surroundings. Where is that angle? Or what contains that angle? So you look at the surroundings, you look at specific theorems that might surround the shapes around that angle. And from there, you start calculating or look at the easiest solution or easiest path. So in terms of steps. So if we look at B2, we see that B2, first of all, lies on a straight line. It is on a straight line. There is B3, there is B2, there is B1. And another thing is that B2 is in this triangle. Triangle BDE. So we go B2 in straight line AC. It is also in triangle BDE. Also in triangle BDE. Why am I mentioning B2? Because the most important thing in here is to make sure you get the method, but everything or the method comes from the thoughts. How do I go about thinking about all of these things? So you ask yourself every time, if I were to focus on this angle, how much effort should I put in finding everything so that I can get this angle? So you remember I mentioned D2, and there is nothing that at this current moment that relates to D2. D2, we don't have D1, and D2 is not in a special position. If we look at B2 specifically here, it is in a triangle. And we notice that in this triangle, which is the second point, and this triangle happens to be subtended by this diameter. This triangle has a line, or has one of its lines being a diameter, and therefore this angle is on the semicircle. So it's on the other side of the circle, and this side we have the first part of the circle, and this side we have the second one. So what cuts those two is the diameter, and this diameter subtends this angle B2. Alright, so we have another point in there, that B2 is special in that it is subtended by a diameter. So we note that. And this semicircle. Alright. Okay, so if we have to find B2, do we have M1? No, we have to calculate M1, but that's not the end of our approach to proving that something is cyclic wire. We have the first approach, we have the second approach. If we were to go for the first approach, we'll have to first find B2, and then we have to find M1 and prove that those two add up to 180 degrees. So that is almost, the minimum is 3 steps in there. So 3 steps. If we go for the exterior angle of a cyclic quad, since we know we can find B2, that's the first or the minimum being 1 step, we need to also find which is the exterior angle that this is opposite on. So for this angle to be opposite an exterior angle, this must be the exterior angle. So this is the exterior angle, and this angle is opposite that exterior. So this exterior angle is equal to the opposite interior angle, is opposite to that angle. Okay, so this B2 doesn't relate to F1. We must always look into the major component of this theorem, that it must be the opposite interior angle. So this is not opposite this angle. It will not always assume this shape, but the general rule is that this interior angle, the opposite interior angles are supplementary. That's the way we go about this. So also that this interior angle is equal to the exterior angle relating to that opposite interior angle. So it's a lot of English words, but you just need to get a grasp of this and practice. Alright, so which is the opposite interior angle in this case, and which is the exterior angle? Exterior angle, first of all, needs to be outside of the quadrilateral. So there is M2, it is outside of this quad, which is the opposite interior angle, is B2. So we already have the value of M2. So this is equal to a minimum of 2 steps. So we already know that our approach will go with the second one. So let's find the value of B2. Like we said, B2, angle B2 is equal to, if this angle is in a semicircle or is subtended by a diameter, we must always know that it is a theorem. There's a theorem that says an angle subtended by a diameter is equal to 90 degrees. This angle comes, or this theorem comes from the fact that an angle at center is twice the angle at circumference. And therefore B2 is equal to 90 degrees. The reason being, angle subtended by diameter, and you name the diameter is DE. It's 90 degrees, but we know that M2 is also equal to 90 degrees. Therefore, because M2 is equal to B2, it therefore means that this indeed is a cyclic quad. Therefore, F, B, D, M, we have just satisfied this second rule in there, that the exterior angle is equal to the opposite interior angle. So when we say FBDM is a cyclic quad, what was the reason? What is the founding reason for our statement in there? So FBDM is a cyclic quad. The reason, opposite interior angle, or the exterior angle is equal to opposite interior angle. So this is a sign for an angle. Alright, so we've proven that this indeed is a cyclic quad. Alright, so let's move over to the next question. Alright, the second question is asking us to prove that angle B3 is equal to angle F1. So just the normal approach, because we're dealing with angles here, we need to first know where the angles are. That's the first thing. And then we look at the surroundings of the angle. So what shapes surround that angle and what theorems relate to that. Okay, so let's find B3. B, then there is B3. So B3, information about B3. B3 is also on that straight line. See, in a straight line, wait, what is that straight line? Is AC. Straight line AC. Okay, and what angle relates to, or what theorem relates to a straight line? We all know that angles on a straight line add up to 180 degrees. Okay, that's the first one. But also, B3 is in a triangle ABF. It's also in triangle ABF. What is the last part? We said it's in a straight line, we said it's in a triangle ABF. But we notice something different about this angle, in that this angle is not fully in the circle. This angle is between a tangent. There is the tangent and this line here, BE. So part of it is outside of the circle. So that angle is between a tangent and this chord BE. So it's also between a tangent and chord. That last statement tells you everything. This angle is between a tangent and a chord. So we start with the first one. What surrounds a straight line? It's the same reasoning that the angles in a straight line will always have to add up to 180 degrees. It's also in a triangle APF. What do we know about triangles? Angles on a triangle should always sum up to 180 degrees. The last guy. Please suggest or just think of what surrounds that statement. I'll give you just a second. Yes, you are right. So when we talk of an angle that is between a tangent and a chord, we always know that that angle will always equal to the angle. So angle, the opposite interior angle that is subtended by that very same chord. That is a theorem. All right. So this is a plus for us. So where is F1? So that's the second one. Where is the angle F1? Let's locate F1. F1 there is F1. That is not equal to 180, so that there is F1. Okay, now that we have located F1, what surrounds F1? So it's the same thing that we stated in there. So F1 is on two straight lines. We see that there's a straight line AM and there's a straight line PE. So it's in a straight line AM. It's also same line. The line is called BE. Okay. It's also in a triangle. You see that there's a triangle in here called EFM. There is that angle. Triangle EFM. This is the triangle we're talking of. It's in this triangle. Alright. Now, it's in this triangle, what else surrounds this guy? Oh, we see that there's this nice circle here. And this angle, the same as M2, this angle F1 is an exterior angle of the cyclic quad. Because we've just proven that indeed FBDM is a cyclic quad. So this angle F1 is exterior, is an exterior angle of a cyclic quad. All right. Now we get to the action. So you read the first statement. The statement asked you to prove that P3 is indeed equal to F1. How do we go about this? We first locate these two angles, look at what is special about them, and solve the question. So we've already seen that for straight line AC, where B3 is on, there's a redundancy of information. We always need to, the goal here is to find the relationship between P3 and F1. So straight line AC usually has the angle P1, P2, and P3. We don't have the value of P1. We've just calculated or proven P2 that it is equal to this one. So if we can try and relate P3 using this or relate it to F1, that is a plus. But we'll need to first of all determine the angle P1. Then from that P1, we need to use the fact that it's in a straight line AC and then make sense of that. So from there, we still need to prove the fact that P3 is related to F1 through this angle. So there's a lot of ambiguous step. Where you see ambiguity, you don't go for that step. You run away. So we already know that this guy, we can't go for this one. If it's in a, we just mentioned that P3 is in a triangle ABF. So there's a triangle ABF. Now we are talking. If P3 is in a triangle ABF, we know that angles of a triangle sum up to 180 degrees. Okay. So, and the most important angle in here is that there is F3. F3 relates to F1. Okay, so let's start. We have B3 in there. We need to find the value of F3. And if we can prove that this angle is equal to this one, if we can prove that this angle B3 is equal to this one, then we already know that since F3 is opposite F1, so we know that rule of X, because if we have an angle here 1 and angle 2, these two angles sum up to 180 degrees, these two. So if you have this one, then you can find this one by saying 180 degrees minus this angle in here. But the same thing also applies that if we have this angle in here, to find this one, we need to say 180 degrees minus this angle. So these two angles are equal. This is a theorem. If you want us to go through that theorem nicely, please put in the suggestions in the comment section below. So we already know here, this is the basis of saying that F3 is equal to F1. So we already see that we can find the value of F1 and relate it to F3. Then if we just need to prove that F3 is equal to B3. So how many steps we need here? We need to find the value of A. We need to find the value of, we need to prove that this angle F3 is equal to this one, and then we need to say we have the value of B3. So we have a minimum of about 4 steps. We're looking at 4 steps there. Then the last one, the angle between a tangent and a chord. So this angle B3 is between a tangent, tan chord theorem. So how about we ask ourselves, what is, because an angle between a tangent and a chord is equal to the opposite interior angle that is subtended by that very same chord. So there is the tangent and the chord. This is the chord. What angle does that chord subtend? So to subtend is to conceal. So this is the chord, and it subtends the angle of D2. All right. So we know that it's relating to D2. But what do we do with that information? How do we go about proving that D2 somehow links to F1? All right. We can hold to that thought. So we don't know yet how many steps we need to go for that. But looking at all of these suggestions in here, it seems as though triangle ABF might be solve our questions, but we don't know. So let's go on to F1. Maybe we might find something interesting. So straight line AM, we need to find the value of F2 here, and we need to relate angle F2 to B3. So it's still a lot of ambiguity here. We don't have the value of F4, we don't have the value of F2. So in either sides here, we need a minimum of 2 steps. We need to find F4, we need to find F2, and then we need to relate this angle to B3. So it's a lot of stuff. But we also see that the angle is in AFM. There is EFM. F1 is in the triangle EFM. How does this triangle relate to B3? We need to find the value of this angle and then calculate the value of F1. From that value of F1 we're getting, we need to do the same thing in here. We'll calculate the value of B3 and then prove that these indeed are equal. So we're looking at an ambiguous number of steps. We don't know where we're going to start with that, because we don't, first of all, have the value of F1, and we need to find the value of E. All right, so the last one. The last suggestion is the exterior angle of a cyclic quad is equal to the opposite interior angle of that cyclic quad. Okay, that's interesting. So F1 is an exterior angle, and this is D2 is the opposite interior angle of that cyclic quad. Okay, we've just seen that D2 relates to F1. So that angle, the interior angle is D2. Bingo. So we see that F1 is related to D2 and B3 is related to D2. So let's execute. This is our go-to area. We need to find D2, which is related with that theorem for B3, and also in here D2 is related to F1. So we calculate B3, angle B3 is equal to angle D2. This is a angle, so it's a tan chord theorem. Tan, what is the tangent? It's AC. Chord, what is the chord? We mentioned that the chord is BE. Theorem. We mentioned that B3 and B2 are related with the tan chord theorem. That the angle between the tangent AC and the chord BE is equal to the opposite interior angle of a triangle. That angle must be subtended by the very same chord. But we also know that F1, angle F1 is equal to D2. This is the exterior angle of cyclic quad is equal to opposite interior angle of that cyclic quad. So therefore B3 is equal to F1. We have just proven this guy. That's it. Let's move over to the next question. All right, welcome back. We are moving over to the next question, 10.1.3. The question is asking us to prove that triangle CDB is similar to triangle CBE. Where are these triangles? CDB, CDB, that's the triangle. We must prove that it is similar to triangle CBE. That is the triangle. All right. Is this big triangle in here? All right. I will attach also a link where we went deep into what distinguishes similar triangles, what can we use to go about to prove that indeed triangles are similar. And the same approach we'll use in this question. So first of all, we must outline what theorems we use, or what sort of approaches or pointers we use to prove that two angles are similar. We can either prove via angles, the angles approach, so all angles. And then we can prove by side angle side. So we need to find the side and an angle in the side. We prove that those are somehow related to the other triangle. Or we can go with full sides, side, 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 side. So we can go about proving proportionality. So where there's similarity, there's a difference between equal triangles and similar triangles. When we talk of similar triangles, we mean proportionality. In that if you were to take the like one side of a triangle and scale it or divide it with a certain side that is so the related side on the other triangle, then the factor will equal to the same applied to the other sides that are left on that triangle. So that is proportionality. So that is where we can go about, and if we say we're proving that the triangle CDB is similar to CBE, we can go with the sides approach and prove that indeed those sides are proportional. But the pointers to that is we must know the values of those sides, or we must at least have some foundation that we are going to use indeed to scale up the sides. It's just hard to scale something that you don't know the value of. And then for side angled side, same thing applies. We need to know the value or find how those, like the sides relate to the other sides of those triangles that are involved. But the angle, we can always figure that out. The angles approach, I always suggest that before you try and venture to these guys in here, try and verify that you can't use the angles approach, because with angles, I'm not saying you can't go wrong, but you won't be confused. You are trying to locate angles that are existing. So the angles, you must prove that the very same angles are in the other triangle. So those two triangles must share the same angles. All right. For this approach, we need to verify which are we going with. We can either go with proving that sides are proportional. There is BCE, there is CDP. We need to prove that these sides, somehow, these guys are proportional. And like I was saying, there are no values in here. For instance, if we had DE as 5 units, BE as 10, then we can go about taking the 10 and dividing by the other one and proving that those have the same factor. To further understand this approach, please consult the previous video that we looked on specifically for circle geometry combined with proportionality. All right, for angles, which I always want us to go with. For angles, we need to find angles that are in CDB that are also in the same as CBE or BCE, whatever you will use to name that triangle. All right, so the first thing you must note is that if we draw this guy, we have a triangle like this. Okay, let's use a different color. We have a triangle. Okay, that triangle has C, D, and B. We have another triangle. Try to draw them out. All right. So let's go with angles. How do we locate angles that are similar in that triangle? So the first one, we can already see that, you know, there's C here and then there's C. But that doesn't always mean that those angles are the same. We must locate that there is no, this angle indeed is the same as this one by looking at this diagram. We can see that this angle indeed exists in this triangle and also exists in that other triangle. So what other cases would it be different? Let's say that more like B. Do you see that there's angle CBD there, and then there's angle CBE. This is B and this is B, but this B in here relates to B1, which I should rightfully note as B1. B1, but B, the other B, relates to B1 and B2. So those are not, this is not the same case for C. So we can already tell that angle C is equal to angle C, that is common angle. That's a common angle. So we already have one angle and we need to look for one last one. Okay, so in here we can't tell much. We can't say B is equal to this one. Or I should say, the point is that you can already tell that B, this B in here is not equal to this B. Okay? Now what does that tell us? Nothing. But we already know that these guys are not the ones that are relating. So we need to find that D relates somehow to the other angle in there. So, okay. We also see that if B1 is not related to B1 plus B2, it can either mean that B1, so this angle in here, B1 plus B2 should equal to angle D in there, so CDB. We can't prove that, but we're already knowing that B1 can definitely not be equal to B1 plus B2, because B1 plus B2 contains B1 and B2, so that can't definitely be equal. So it means that we must prove now. What we have left is either to prove that indeed D is equal to B1 plus B2, or B1 is equal to E. So which is the easiest? So we must look at how those two relate. Let's start with B1 and see how it relates to E. Okay, where is B1? Please use the same approach that we used on the previous questions. Now we're going to do it a little bit faster. We won't be putting in where is the location of this, what surrounds that angle. We will be doing all of this through a conversation. So B1, we see that B1 is falling in this straight line, and that straight line is a tangent. And B1 is not inside this circle. B1 is not inside this circle. It is between a tangent and a chord. Tan-chord theorem. So this angle B1 must somehow relate to E. The theorem that says a tangent and a chord, the angle between a tangent and a chord is equal to the opposite interior angle, relates two angles. We found the first one. Now we need to find which is this interior angle that is subtended by that chord. There's the chord DB. What angle does it subtend? E. That's it. So we've proven that angle B1 is equal to angle E tan chord theorem. So what is that tangent? You name it. Tangent is AC, and what is that chord? Is DB. All right. Therefore, triangle CDB is similar to triangle CBE. We have proven our question. If you have any questions, please drop them in the comment section below. Don't forget to like, subscribe, and recommend the video to anyone in need. And we are not going to continue with this question. We'll divide this video into two parts. The part that will address the last two questions, and make sure try and finish this one first and then have a look at the second one, because definitely the second one will need this information that we used on this first video. All right, let's go.